Good afternoon, everyone. Welcome to the SETI Institute. I'm Tom Pearson, the CEO, and I'm standing in for our lecture series coordinator, Adrian Brown, who's in Washington, D.C. today. It's my pleasure to welcome you to the next in our regular series of science symposia that we have Wednesdays at noon, most Wednesdays. I want to mention a couple of ground rules just so you understand how we're going to proceed. Number one, when we get to questions and answers at the end, let me hand you this microphone, and you'll probably go, and you'll wonder why it's not broadcasting through a speaker. It's actually recording into our system. It is not going to any speaker system, so please speak up with your questions, but you'll also use the microphone to record your questions so that it will be on our website when we post this lecture as part of the symposia series. I also want to mention next week's program, which will be Dr. Eugene Lally, who is one of the earliest members of the United States spaceflight program, and he will be speaking on how spaceflight was born. So at this point, it's my pleasure to introduce our two speakers. I'll do a little bit of bio on each of them and then introduce them in order as they proceed. Our first speaker will be Dr. Jill Tarter. She is the director of our Center for SETI Research. She holds the Bernard M. Oliver Endowed Chair here. And Jill received her degrees, a bachelor's degree in engineering from Cornell University, and both an MA and PhD from the University of California, Berkeley. She is well known, I'm sure, to all of you as the leader of the SETI Institute's SETI program since our founding in 1984, when she was one of the co-founders of the Institute. Jill's received many awards during her lifetime. Two of the most prominent that I will mention have occurred recently in the 21st century, when in 2004 she was named by Time magazine as one of the 100 most influential people in the world. And very recently, Jill learned that she will be a recipient of the 2009 TED Prize, Technology, Entertainment, and Design, which is with that prize, Jill received a nice monetary award, which she has informed us that she is going to be donating to her program here at the SETI Institute. And she is also granted one wish by the TED Brain Trust, one wish to change the world. And so we are all eagerly awaiting Jill's February 2009 announcement of that wish. Our second speaker will be Dr. Don Backer. I've had the pleasure of knowing Don now for the last 9 or 10 years. Don is a longtime radio astronomer at the University of California, Berkeley. A very distinguished career. He received his degrees from Cornell University, studying under an advisor that a few of us have heard of. His advisor for his PhD was Dr. Frank Drake, hiding over there by the wall. Don just recently stepped down from the role of chairman of the astronomy department at University of California, Berkeley, and stepped into the role of director of the University of California's Radio Astronomy Laboratory, and also into the role of director of the Allen Telescope Array. And so we will hear from Jill first, and then from Don. The title of their talk is The Allen Telescope Array, a radio survey telescope for the 21st century. So, Jill.
Well, thanks. It's a pleasure to get to talk to you guys today and tell you about this new instrument that the UC Berkeley and SETI Institute have been partnering to build for a while now. And it's just beginning to take off as a scientific instrument. So I'm going to tell you about the SETI surveys that we're going to do with that telescope. And I'm talking for the group of people that I get to work with here at the SETI Institute, and then some consultants who are parts of the program. We need a couple of things to start doing SETI on the Allen telescope array in addition to the telescopes. SETI needs beamformers. I've talked here before and explained how an array of 6-meter antennas looks at a very large area on the sky at any one time. And the radio astronomy folks the astronomical searches can be made by making maps of that large area of the sky, radio images, at the same time that SETI or other people interested in looking at point sources can use beamformers to pick out individual pixels on the sky that they want to study. And ultimately, we hope to have at least 8 beamformers that can be used, which means possibly 8 stars at once that I could observe for SETI. At the moment, we have 2, and we have this summer reached a very nice milestone. You can see on this diagram the Voyager 1 and Voyager 2 spacecraft, which are actually leaving interplanetary space and heading out into interstellar space. On the 15th of December in 2004, Voyager 1 passed through the termination shock, and then last July, we used the beamformer with 12 of the 42 antennas phased up to detect the transmitter from that spacecraft. And indeed, if you've got good eyes and you really believe, you can see on this waterfall plot Voyager 1 signal. But you don't have to believe. What you can do is use the SETI signal detection hardware, which averages or which adds up all of the signal along this path and provides a very strong, oh, you want me to stand here because the camera is there. I'm sorry. A very, very detectable signal from a transmitter which has less than 10 watts of power at over 106 astronomical units, 106 times the distance of the sun to the Earth. So this is a very weak signal, and it's a very strong detection in our hardware. And it's a very good check that we've built the beamformer correctly. This is at a high frequency. It's at 8 gigahertz. Everything gets harder to do at higher frequencies. So it's a good check of the beamformer and our SETI signal detection. So we've met this milestone of getting the 2 beamformers on the air. And the next thing that we need is a large catalog of stars in order to be able to do this commensal observing, so that in any field of view that the radio astronomers choose, we will always have interesting SETI targets to look at. So what I've plotted here is the average number of stars per field of view visible at Hat Creek in Northern California, where the telescope's being built. And if you haven't checked it out, the bottom is a panorama of all of the telescopes at Hat Creek as a function of frequency. And this line here would be on average 1 star per field of view, and this is 3 stars per field of view. And I've drawn 3 lines. If you happen to have a catalog of 17,129 stars, which we do, we built it with Maggie Turnbull over the summers and as part of her PhD thesis. We call it the HabCat, the Catalog of Habitable Stellar Hosts. Then along this curve, this is how many stars you'd have on average for field of view. And with this small number of stars, you only have as many as 1 star up to a frequency that's about 1 gigahertz. If you happen to have a catalog of 250,000 stars, which we do, it was the HabCat 2 that we built with Maggie using the HabCat 1 was from the Hipparcos spacecraft. HabCat 2 uses stars from the Tycho catalog. Here you can get up to 3 stars per field of view on average, up to about 2.5 gigahertz. And really what we want is a catalog of 1 million stars, and that's being built. Peter Backus is worked with an REU student last summer, and will work with another one next summer to work on a catalog called NOMAD from the U.S. Naval Observatory to build this larger catalog of 1 million stars. So these are our 2 requirements, and we're well on our way. And then you add them to this fantastic instrument with its small dishes looking at the Andromeda galaxy here, a nice optical picture. Here's for scale, half a degree across the moon, 3.5 degrees divided by the frequency in gigahertz field of view with the Allen telescope array. And here's the first map, the first astronomical map that was made with the telescope. And here's what happens when you put the stars that from our catalogs in front of that field of view. This just gives you an idea of how this commensal observing works. And you can see there are 3 Habcat stars, there are 45 Tycho stars, and about 200 from the NOMAD catalog. So this is a very doable kind of commensal project. And as I said, we hope to have as many as 8 beams at once, which would mean 8 stars at the same time, which really speeds up the searching. And we've begun the commensal observing not with M31, but with M81, this galaxy here, M81 and M82. And last summer, while a map was being made of M82 here, we began observing a total of about 50 stars in front of that galaxy. And with a sensitivity that is, when we have the full 350 dishes, which we have 42 now, the sensitivity would be adequate to pick up an Arecibo planetary radar at about 300 parsecs. So to get really started on systematically surveying what we think will be about 1 million stars over the next decade, we need a third beam and a ring or a null beam. So here's our strategy at the moment with 2 beams. It's what we started with the M81 field. We do a target observation, right? And we try and build up a database of known interference. And we're just starting, so our database is empty. But when we're observing, we find signals, and we say, are they in the database? Are they known interference? If not, we're observing 2 stars at the same time, and so we say, okay, was this signal seen in both directions simultaneously? If so, it's coming in the side lobes and it's interference, and it's not an interesting signal. If it passed both those tests, we say it's a candidate, and we do another on observation. This is to rule out, we use a fairly low threshold, and so noise alone can trigger our detection criteria. So we do another on observation. A noise event will not trigger again at the same point. We again do the 2-star comparison. And if it passes the test, we observe off. And if it's seen off in either of the 2 beams, then it's, again, an interfering signal. If it's not, it becomes a candidate for further tests. So when we did the M81 observations, we did 25 observations of pairs of stars. You can see that we found a lot of signals. Only 139 of them became candidates. And the second on observation eliminated all but 1. And that was eliminated with an off observation. So the pieces are all gelling. It's just not yet efficient to start. So what we have to do is add nulls to our strategy. You can form a beam with the beamformer. You can phase up the telescope to look in a particular direction. Right? Here you have peak sensitivity. You can also at the same time form a null. At an arbitrary place on the sky, you can arrange it so that there's a very deep null, and you see no for minus 27 dB, right, almost a factor of 1,000 down in sensitivity from the main beam. So what we do is we put star 1 in the peak of this beam, and star 2 we place a null. And then you repeat this with the second beamformer, where star 2 is at the peak and star 1 is in the null. And then when you do the comparison and you say, was the signal seen in 2 beams simultaneously, there is a small possibility that a real signal coming from an extraterrestrial transmitter on star 1 could fall into the side lobe of the beam formed on star 2 and therefore be detected and thrown out when it really shouldn't. So the extra step of putting a null on the second star gets rid of that. And so we are beginning to crank up this particular improvement to our search strategy. And our goal is 1 million stars over 1 to 10 gigahertz using HabCat 1, 2, and 3. And so, as I said, this is still in progress from the NOMAD catalog. We're also going to do some surveys of the galactic center region. And basically, we're going to look at 20 square degrees surrounding the galactic center. Along those lines of sight, there are about 4 to 10 billion stars. And a transmitter would have to be very strong because most of those stars are extremely far away. Maybe something like 25,000 times as strong as the Arecibo radar for us to detect. But we've not done this job. It's an awful lot of stellar targets in a very small region of the sky, and so we will do that, and we will do it by taking our beams. Here I've shown 2 small beams. Hopefully, by the time we start this, when the galaxy rises next March, galactic center rises next March, we'll have 3 beams that we can sweep through the large field of view. And basically, again, the interference rejection is to take 1 degree by 1 degree squares, grid them up, and here are the beam spacings that we will use. And then you chose 3 beams separated by more than 2 beam widths. And you use the beam and the nulls, and you try and make sure that anything that's seen in more than 1 beam is rejected. And you just let the computer pick out among the 3,519 potential target directions which ones are up, which ones haven't been seen yet, which ones are far enough away from the sun to avoid spreading a signal by passing through the solar wind. And eventually, in about 6 months, you can complete a galactic plane survey. And while we're doing that, there will be a commensal observing program going on that has been proposed by Joe Lazio and colleagues at the Naval Research Lab, and some students looking for radio transits while we're spending all this time searching the galactic plane. The other kind of survey that we're going to do very quickly is a survey of, I haven't updated this slide in a month, but a month ago it was 155 stars hosting 186 planets. So looking at the known exoplanet systems and doing a water hole survey probably take only about 65 hours to get that completed, and we'll do that more than once. So those are what are on the schedule for the SETI Institute observations, but there are also observations that will be done with the telescope that have come in from external proposers. So this is a search for Dyson spheres. Those Dyson spheres, artificial constructs intended to collect the majority of the stellar power for purposes of an advanced civilization. And they've been picked out of the IRAS catalog and will be, again, a water hole 1420 to 1720 megahertz search of these targets over about 30 hours. An external ecliptic plane survey, and I don't have Seth's name on here because we were really billing this as an external proposal coming in from Johns Hopkins and Ball Aerospace. And Maggie Turnbull is also signed on to this as someone. I think Maggie's going to be the one that does the data reduction. The idea is that if we expect another civilization to be transmitting towards us, then we ought to use or look for those transmitters among stars that would have a reason to know that we're here. And if indeed they have the equivalent of a terrestrial planet finder or a Kepler spacecraft, then they will have noticed the Earth in transit in front of the Sun. And those stars are all located in the ecliptic plane. And so there will be a search of the ecliptic at opposition for the Habcat stars. And so far, we've assigned about 15 hours to that project. And this is actually an update of an old idea of some Russian colleagues of ours. So the ATA the ATA 42 may soon become give us the answer to life, the universe, and everything. And the 42 reference is not lost on some of you, I can tell from the chuckling. But in fact, there are some other ideas for SETI searches that have nothing to do with the ATA 42. I thought I'd like to talk to you about some of those. There are a lot of astronomical observations that are being made, and now astronomy is getting into big surveys. And some of those surveys might, in fact, turn up a signal that was almost natural, one that was engineered to look sort of like a natural phenomena, so that when we begin, as an emerging technology, looking at the universe and sending out or using a net to capture astronomical targets, we will also capture these almost natural signals and eventually realize that something strange is going on with them. So one type of signal, okay, let's see if I can get this a little louder. All right, one type of signal that we're surveying the skies for are pulsars. And pulsars occasionally undergo starquake, and they change their absolutely precise period to another period. But pulsars never naturally do this. One period, another period, and back again, forth again. But if indeed in a database somewhere we were to find a pulsar that switched its period between two values back and forth, it would be a very good indication of somebody else's technology. All right, we are going with Kepler, we're going to look for a planet like the Earth transiting in front of a star. But it doesn't have to be a planet. In fact, the star could be blinking because of some large engineered structure intended to transit across the surface of the star and in an ecliptic plane provide a transit that looks funny. So there is enough information in the higher order modes of the transit light curves to distinguish something that's round from these shapes which are shown here with their light curve. So indeed, something like a Kepler. Remember this, Edna, right? We have to keep this in mind when we're looking at Kepler data. And John Jenkins is here too. The higher order terms here might in fact be indicative of a transit that's engineered. And lastly, an interesting idea that just got published a month or so ago. There are on the sky variable stars, Cepheid variables, whose have a very precise period, and their period is related to the luminosity of the stars. These have become very good distance indicators for astronomers. It was pointed out that if you wait until the star is at its most compact and then shine a beam of neutrinos in there at just the right time, you can advance the phase of the next pulse. So you in fact can create what is difficult to understand how could otherwise be created, an omnidirectional beacon with a binary code, a short pulse and a long pulse. It would take a long time to transmit information because the periods on these things are days to weeks. But in fact, you might be able to embed information in the pulses of a Cepheid variable. So I've talked with Jeff Scargill, who has a lot of data on Cepheids and who is a master at finding periods. in various astronomical phenomena. And so perhaps this summer we'll be able to use a summer student to search through some old Cepheid variables and give this idea a try. So I'm going to turn it over to Don now to talk about astronomical surveys, but you can see what's on the plate for SETI in the next couple of years. So Don, it's yours.
While they make the change over to the next computer, I thought I would mention, first, Jill, I spilled your coffee as I stood up there, so I apologize. But I thought I would mention that back in the days when the concept of the Allen Telescope Array was put together by an advisory team, and the volume that was produced from that was called SETI 2020, it was recommended that the SETI Institute proceed with building a telescope of large numbers of small telescopes, build an array, and that we needed to find a partner who had experience in building telescopes and running an observatory facility. The decision was made very early on to partner with UC Berkeley, and I think we're very fortunate to have Don assuming the role just this past summer as director of the Radio Astronomy Lab and director of the ATA. In just a few short months, he's shown an amazing degree of leadership, and I want to personally thank you for that, Don, and the floor is yours.
Okay, thanks. I hope you're all comfortable in your seats. I gave a 30-minute presentation up at the Allen Foundation last Wednesday, and it took 2 hours. The talk I'm going to give, as said, is about the astronomical use of the Allen array, and I'm here representing the list of people here up at Berkeley, some who've yet to arrive at Berkeley. First thing I want to say about this is that the Allen Telescope Array is a tremendous survey instrument. As opposed to target, look at that star, look at this star, surveying the heavens broadly is one of its main purposes. And we characterize this by giving the speed, got my finger on that, the speed of the survey in degrees per second as a function of radio frequency, and comparing that to the other large telescopes in the world. The dashed lines are the telescopes that exist, and here's the ATA 42 ranking up there with the world's largest telescopes because of its design, because of building the large number of small dishes as opposed to large dishes or large dishes in small numbers. The solid lines are where the world is going, and this includes the Allen array and as well as Australian, South African, and the U.S. extended expansion of the VLA. And if we get up into the, when we get to the 128 level, we're clearly up there ranking with these other large apertures that are coming over the next 3, 4, 5 years. And if we, I have to keep on target here, when we get to the 256 and 350 levels, we'll certainly be top in the world for doing these kinds of surveys. And the surveys are really one of the things that's driving science now, feeding the investigation of the heavens in all these different wavelengths from the radio all the way up into the gamma ray region. So here's my outline. I've got a tall order to run through these different astronomical cases that are starting up with the ATA 42. I'll do my best to run through that this list and give you a little flavor of each of these. Put my clock up. Oh, we've got a clock there too. They range quite a range of topics, and I'll give you just a flavor of each of them as I walk through this list. The first and one of the prominent ones, and one of the areas that can be done profitably with the ATA-42 as it stands and break new ground in science is surveying the sky for things that go bump in the night. The universe is full of explosive phenomena. They are characterized by this accretion matter flowing onto compact degenerate objects, neutron stars and black holes. This is over here on the right is what would happen with a star as it comes in very close to a massive black hole in the center of a galaxy. It just gets shredded apart by tidal forces, and there are various calculations of what would happen in terms of bursts of electromagnetic energy across the spectrum. The radio component of that is somewhat speculative, but we know this phenomenon happens, and that's one of our targets. The diagram over here is a kind of poor cartoon of what would happen or what is happening with stars that under special circumstance collapse probably into a black hole and emit jets of gamma rays. If the gamma ray jet is pointed towards us, then the satellites can pick that up. It puts out a tremendous burst of light. It can be seen across the universe. And when that energy flows out and hits the circumstellar and interstellar matter around it, it glows in gamma rays, it glows in optical, and it glows in the radio. Well, if the gamma ray jet is not pointed towards us, we don't discover it, but we can still see it coming into our sky when this matter hits the circumstellar environment and light up in the radio waves. So it's known as an orphan gamma ray burst. And there are other objects. Importantly, when you open up a new window of scanning the skies for blinking phenomenon, we expect to find the unknown. It's just a jungle out there. It was a jungle when I started 40 years ago, and it still wonderfully is a jungle, and we look forward to the unknown. This work has motivated, this is led by Jeff Bauer and his postdoc and students at Berkeley. It's motivated by a piece of work that he did with the VLA, where he's already scanned a very small piece of the sky, but a large enough piece of the sky for enough epochs in time, to turn up a few of these blinking events. And I'm not trying to communicate a whole lot with these pictures, but the sources in the center were transient sources that were there in one epoch and not in others. And these are optical follow-up observations looking for what might have been the host of where that explosion took place. And so Jeff is very convinced that with the sensitivity and the speed of the ATA-42, that he can get into the business of making new discoveries in the year ahead. And that's very important for the array in its early stage. So it's referred to as FIGS, the 5 gigahertz sky survey. It's a counterpart to the optical Sloan digital sky survey. It'll overlap in the geographic part of the space, doing about 10,000 square degrees. It can compare the results of this to other radio catalogs, which are these two, NVSS and FIRST. It'll be the first high-frequency, deep, large radio survey that's going on for some time, reaching down to the Millijansky level. This is a factor of 10 times more sensitive than the venerable GB6 survey. This is one done with a 300-foot telescope in Green Bank, the Green Bank 6-centimeter survey. That Green Bank telescope has collapsed 20 years ago. And will take about 6 months to complete. The arguments one of the arguments that, for the growth in the size of the array is to be able to do this on shorter time scales. These explosions they come on for a day or days, and hence you want the cadence of your scanning the sky to be matched to the astrophysical time scale of the phenomenon. So the driving force to get up to the larger arrays is to make the power of the instrument match the physical phenomenon that we're looking for. phenomena, plural. Here's a test survey. This is work. There's some 350 different pointings with the ATA-42. All these little dots in here are real. There's a blow up of a little region. These are all extragalactic sources, what we call active galactic nuclei, the matter falling onto a massive black hole in these distant objects. And it's making images like this and then blinking them from successive observations. That will be the effort in this work. This is doing, the startup work is being done at 20 centimeters. It's a little easier. The goal is to move this up to 6 centimeters wavelength. This is a panel of a special use of the ATA that came up, actually came up a year ago during the dedication. That Jeff Bauer was talking with Jim Cordes, a colleague of ours, while they were getting dessert, during the dedication, and a phenomenon had just been discovered and announced in the community of a single pulse that rose to incredible strength. It had dispersion to it. Looked like it came through a tremendous amount of interstellar, intergalactic plasma. The direction that they were pointing was indicative that this was an extragalactic pulse, not even an object in our galaxy, and that just got all our juices flowing. The group of people in and around Berkeley had a few discussions and said, well, gee, we could get the equipment together rather quickly. We could point our ATA-42 in 42 different directions, unlike its nominal purpose, and scan the skies very rapidly for these kinds of pulses. The possibility of detecting something was a little limited in terms of sensitivity. It would have to be brighter than this pulse that was announced a little over a year ago, but this was a new game, and here we had the ability to do this, and so that all happened very quickly in terms of putting hardware together. Jerry and others helped, point the telescope in 42 different directions and just park it there and cover the large piece of sky for many hours. No pulses have been found. A publication is due to put this limit out there into the astrophysical literature. Unfortunately, 6 weeks ago, the group that did the original discovery of that pulse is in the process of retracting this. It is now probably interference, although one of the most mysterious pieces of interference that we've seen for a long time. Move on. If you're scanning the sky looking for these transient pulses, you're also building up a catalog of the sky, of the static sky, what's always there, these active galactic nuclei. The power of the ATA is that it can observe across this full microwave bandwidth from 1 to 10 gigahertz. So Peter Williams is a student working with Jeff Bauer. So each one of these sources, one can get the full microwave spectrum and tackle some of the physical processes that are actually producing that emission. And Peter's often running with this effort, which will go on with these surveys. Talk a little bit about pulsars. The pulsar is you heard Jill mention it earlier. It's a rapidly rotating, highly magnetized neutron star. It's spinning. It has a magnetosphere around it. It generates currents along its dipole axes and spinning. And like the gamma ray burst jet, if we're in the right direction in the sky, we'll see that pulse sweep by us once per revolution. Jill gave you an audio track of one of these pulsars, so I won't repeat the one on the left, which is a slow pulsar. But there's some pulsars that spin almost 1,000 times per second. And if you put that signal into an audio detector, you don't hear the pulses because it's at a a higher frequency, 642 hertz in this case, but in fact that pulsar, you actually see two beams, so it's much closer to 1280, and 1280 is between D and G on the in the soprano bracket of that audio scale. That object is extremely remarkable. Neutron star spinning out there. There's really, apart from the little bit of emission that comes out from that spinning object, there's no friction there. It's a clock, and we can use that object as a clock and potentially detect gravitational waves with it. Now that process is something that would take a few minutes to describe, but let me just jump to the chase. And if you send an electromagnetic signal through space-time that has gravitational radiation rippling through it, it effectively doesn't travel at the speed of light. It's modified by the presence of that gravitational radiation, and that it gets imprinted on the arrival time of that signal at the planet Earth. And one can positively detect this presence of this distortion by the fact that the clock doesn't run quite so smoothly. Furthermore, the clock in this direction and the clock in that direction are anti-correlated in terms of their perturbation. So we use pulsars, an array of pulsars around the sky, as a gravity wave detector. This is entirely the same process as the gravity wave detectors on Earth, known as LIGO, where they send a laser down to a mirror and comes back, and the arrival time and the return is different along this path as along that path. In our case, we have clocks out there. We don't need mirrors, and otherwise the phenomenon is quite the same. The gravitational radiation that we might detect from in this pulsar timing array, the most likely source of this, is the coalescence of massive black holes in the centers of galaxies. And this very simple story that is part of our cosmological view is that galaxies have massive black holes. We know that for sure. Our own galaxy has one in the center. We know them in many galaxies. Galaxies grow by mergers. They come together and coalesce. Dynamical friction is very effective. You bring two massive black holes together in a star and gaseous system, and they will sink together down to the scale at which the binary motion of these two massive black holes will decay by the emission of gravitational radiation. So we know that exists. We know the process exists. Here are a couple of examples of two nuclei, of two galaxies. There's almost certainly two massive black holes. This is a beautiful example, where there, in the radio, there are two point sources down here, both of which have these jets of materials shooting out from them into the intergalactic medium. Those two sources will come together through dynamical friction. The two massive black holes will sink to the center and generate gravitational radiation. And then that is what we would try to detect with our precision pulsar timing. The sensitivity of these objects, the strength of the pulsar signals is such that we really can't get into this game with 42 antennas. You can barely get into the game with 128 antennas. We really have to get up to a equivalent of a 100-meter class equivalent collecting area of an instrument to play this game on the international astronomical stage. The value of the ATA for this is the broad frequency coverage, because the pulsar signals have to come through the interstellar plasma. The interstellar plasma is not uniform in density, and there's essentially interstellar weather, plasma drifting through the line of sight, and that corrupts the view of a distant clock because the path length is not constant. And so we take out that effect by observing at many frequencies. And the ATA is ideally set up for doing that multi-frequency observing. And the other effect of the ATA, of course, is that other measurements can go on at the same time. The transient source detection that I talked about earlier, if the SETI team wants to go back to the same fields, week after week, month after month, they can jump onto the signal paths at the same time, and so this could go ahead. Think about my time here. So next topic is the study of hydrogen in galaxies. The Earth has a fossil fuel crisis. Somewhere in the next, I was generous here, perhaps 10 to 50 years, maybe it was yesterday, that we have a problem with fossil fuels. The Milky Way has a problem too with its star formation. And that's illustrated in these charts here. This is distance from the center of the galaxy out to its periphery. This is where the sun is. And what's plotted at the top is a graph of the gas, or the surface density of this gas, and in red, the star formation rate, the rate at which this gas is being turned into stars. You take the ratio, you have a time scale, and that time scale is less than 1 billion years. Okay, so the galaxy is a dozen billion years old, and it looks like the gas around it, it's going to go away in 1 billion, 10%, less than 10%. And this is what's known as a problem. We don't understand that. We look back in time at the stars that were formed 5 billion years ago, and it looks like the rate of star formation was about the same as it is today. And that's a head scratcher. We like head scratchers in astronomy. They drive our subject. The bottom plot is just a slightly different version of that. And so one of the hypotheses to explain this, which Leo Blitz and his colleagues have put forward, is dealing with the gas in the periphery of the galaxy, outside the solar circle, well outside the solar circle, and how that gas might get in to the center, and to short circuit this a little bit because of the time, what's being driven here is to look for hydrogen in the periphery of galaxies and between galaxies, and that's something that the ATA is well suited to. A couple of pictures here. Down below is the density of galaxies seen in the Sloan Digital Sky Survey. I mentioned that a little earlier ago. Radial distance from the center here is the redshift, or the distance of the object from the Earth, and plotted on here is the number of galaxies. What you see is this filamentary web. The galaxies are not uniformly distributed out through the universe, but they form in filaments and sheets. And if you look at a single galaxy or a small group of galaxies, as you see here, a bunch of galaxies, this is a ATA study of the hydrogen. So there's a lot of hydrogen around this galaxy. There's not much hydrogen around these galaxies. But here's a piece of fluff out there between the galaxies. And that's the kind of survey that Leo and his students want to do. They've made some progress with ATA 42. Here's a Jill put up earlier, the M81 group. Here's M81, M82 in the optical. This is the hydrogen map. This is a week or two old. map that Blitz and Keating have been doing, and gives the distribution of hydrogen around these galaxies. And that's the target for doing this, not just on this group or that group, but do a wide survey to try to understand where this hydrogen is and how it gets into fuel star formation in the center, or not in the center of the galaxies, but in the regular part of each of these galaxies, and understand that mystery of the rate. Let me turn to a couple of studies right here in our own Milky Way. This one has a goal of looking at the molecular material out of which stars form, and the picture on the left here is a nearby, about 1,500 light years away, molecular cloud. It's made up of molecular hydrogen, carbon monoxide, other molecules, and the contours here give that general gas distribution. The stars give the protostar locations, and the goal here is to find not these protostars, but the things that form protostars a little bit earlier in their history, and understand what processes determine this final mass. We're one solar mass. There are stars that are 10 and tens of solar masses, and there are stars all the way down to about 10 Jupiter masses. And one of our long-term agenda in astronomy is understanding that whole distribution. How's that mass spectrum actually form out of the goop in the interstellar medium? And the method that this will be done with is to observe up at 9 gigahertz at the higher end of the ATA band to look at 3 of the quantum transitions in the HC3N molecule, and by looking at those 3 transitions, their frequencies are here, their quantum notation is there. One can pick out understand from the physical, the astrophysics of that process what the temperature is and density in those regions. The ATA is going to be extremely important to cover the wide area that is covered by this nearby cloud. You see it's many degrees, and we can only do a few degrees per pointing. So again, the ATA is well designed to do that. A second activity, and these were promoted particularly by Jack, is looking at what's called the metallicity gradient. Astronomers are very simple-minded. There's hydrogen, there's helium, and there's everything else. And everything else is called a metal. So we want to know that everything else comes from stellar processes, these explosions and cycling matter through stars. The early universe, it's hydrogen and helium, and everything, all the stuff that we're made out of, the carbon, heavier elements, all came out of stellar explosions. I'll wrap up here. One of the challenges is understanding that distribution of matter and metallicity as a function of galactocentric radius as we move out in the galaxy, and how did that all take place, and how do we go back from our current state to the earlier phases. So a little bit of theory about again, looking at these line transitions to back out the physical properties of the objects that are being looked at. These are H2 regions, ionized regions around stars, and the ATA comes in as having this great frequency agility, the large field of view, spatial resolution, to make this a success. And formulae over here give you a little bit more on that method. As with the SETI program that Jill mentioned, we've solicited the community for external science proposals. We were pleased, at the interest. Jumps a little bit ahead of our schedule in terms of our ability to cope with all of these. We've provisionally accepted 14 of these for 450 hours, and I'll take a particular note of one of them that came with a check, or when it comes, it'll come with a check by our colleague who wants to do the study of the magnetic field in the galaxy, while Jeff Bauer and others are doing their study for transients, while Peter Williams is doing his static source survey, and while Jill and her team are doing their SETI. We can do all of those things simultaneously, and that's the big strength and original design of this fascinating instrument. My summaries, then, it's agile, it's powerful, and the current state of things is that this survey is in kind of phase one, that we're trying it out, understanding how stable the instrument is, and to pick a noun of the coming around the corner, the inauguration of these surveys will take place, we think, around January, inauguration month.